Hello? 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 Yeah, I think now. Okay, so let's get started. Back to our schedule. So the next speaker is Adam Moody. So he's a member of the Development Environment Group within Livermore Computing at Lawrence Livermore National Lab. His background is in the MPI development, collective algorithms, networking, and parallel I/O. He's a project lead for the Scalable Checkpoint Restart Library and MPI file utilities. So two projects that use MPI to help manage large data sets. And he has been a Buckeyes fan since birth. Okay, so he's actually like a alumni of the our now lab Mpi group. But I didn't know you were a Buckeye at the birth. I didn't know that.
I've been brainwashed since birth. Yeah, my parents are both Ohio State grads.
Yeah. So he contributed to actually the Mpi project in the very early days, even prior to Infiniman. When he was a student, Quadrix, if you remember, Quadrix was the interconnect that time. So he actually worked on collective offload to the Quadrix. That was his thesis kind of things. So since then, as you said, like he has been attending all the MUGs and bringing perspective from the Lawrence Livermore National Lab. And he also, I think those of you know, like the Buckeyes, the football team here. He actually leads the West Coast. You're chair of the Buckeye.
It's the San Francisco East Bay Alumni Club.
Yeah. So
there's a few of them out there.
Yeah. So there are several alumni clubs. So he leads one of them. So with this, let's welcome Adam.
Yeah, hi all. Yeah, so Adam Moody, I work at Lawrence Livermore National Lab. Within there, I work at Livermore Computing, which is kind of the support side of the house. So our job is to keep the clusters running and to help users run on the systems. It's good to be back at MUG. You know, I attended virtually the last couple of years, but it's always good to be back in person to see everybody. So really honored to get to come back and talk. Today, I'm going to be talking about Mpifyutils, which is a library and a suite of tools that use MPI to help users manage large data sets that they're creating on the HPC systems. And though I'm the president of the East Bay Alumni Club and a huge fan, I didn't know the answer to the trivia question last night, which was Undisputed Way. I think there was one person in the room who got it, and that's Dong Lai sitting here. So congrats to Dong Lai on that. Fortunately, he was on my team, so I got a point for it. Yeah, I'll take it. But okay, so you know, MPI has been around for decades now, and it's really what's allowed people to scale up systems and for users to scale their jobs on those systems. You saw from Dr. Panda's slide, Mpifyutils is 21 years old now. Right, so it's amazing to think about, but if it were a person, that could have actually joined us at the brewery and had a beer with us last night. So anyway, so people have used MPI to scale up to these systems. This is a scatter plot of the top 20 Lustre users for one of our file systems. This is showing the bytes written in a data set and the number of files that they generate in a log-log scale with the bytes on the vertical axis and the files on the horizontal. And so, you know, 2 to the 10 is you're talking about kilobyte size, 20 megabyte, gigabyte. Up there at the 40, you're reaching into the terabyte data set size. And you might be dealing with tens of thousands or hundreds of thousands of files, right? So when you're sort of in that bottom left corner, your standard Linux tools like CP, remove, ls will help deal with those data sets. But once you start reaching that upper right, things become pretty painful. And so just as an example, consider you've got like a large scale simulation that you've run, and maybe that simulation wrote a checkpoint, right? So you have a single directory with 200,000 files in it, each file being 128 megabytes. So that totals up to about 24 terabytes. And now what you'd like to do is just make a copy of that, right? So maybe you want to modify those files in some way, but you don't want to mess with the original in case you mess something up, right? So you just want to do this simple recursive copy. So a few years ago, I actually did that exact experiment. So sometime in the morning, I kicked off a copy and I just let it churn in the background. This was on the login node of one of our systems. Checked back in when it was time to go home. It hadn't finished yet, but it had gotten to to complete about 114,000 of the 200,000 files, right? So it didn't quite reach it, but you can just do some math to figure out like how long would have had to run to get there, and that comes out to about 14 hours. Another way to do that copy is to use DCP. So DCP is one of the tools in Mpifyutils. It's an MPI-based tool. So in order to use it, you have to allocate some compute nodes. So in this example, I'm first allocating 8 nodes from an interactive queue on one of our systems. And then you launch it with MPI run or srun, whatever your MPI launcher is. For DCP to do that same copy, it finished in 370 seconds, right? So for copy, it took 14 hours. DCP is just 6 minutes, just a little bit faster at 140 times fast. But if you think about that, that's a huge difference, right? Because if you want to like make a copy of these files because you're going to do some work on them, on the left-hand side, that means you come in on a Monday and you start that copy, and then maybe it's done by Tuesday if nothing went wrong, right? So you can't really start your work until the next day. With DCP, it's just a few minutes. So it's a huge difference in practice for the user, right? So what's the problem here? The issue is that people are generating these data sets using thousands of nodes, tens of thousands of processes, but then they're stuck managing those data sets with just single process tools, right? Like, so they run a giant MPI job and generate this giant data set, and then they're trying to copy it with CP, right? So it's just this funneling of 10,000 to 1 really just doesn't work, and you have to get away from that. So Mpifyutils, the whole goal of it is to use the same resources of the cluster that the people generated the data set to begin with in order to manage it, right? So it runs on the same nodes, uses the same network, the same file system. It's using MPI, and it's built to sort of deal with all the HPC file systems that you'll find on the standard data center, right? So Lustre, GPFS, NFS. When we started this work, we wanted to look around. We had this idea to sort of build this suite of tools. We wanted to see if anybody had started anything, and there were a few items out there. The one that kind of drew our eye was some work at Los Alamos. There's a group there that created a library called libcircle, and it's a way to, it's a distributed work queue, right, where each process has a local queue of items that it's working on. It draws items from that queue. It might generate new items or new work to put back in the queue, but if it ever runs out, it just randomly asks some other process for work, and it will steal some if that process has some, right? If it doesn't, it just randomly asks somebody else. And so it's a good way to sort of diffuse work across a cluster. They then built DCP, the original DCP, the parallel copy tool, where they implemented all of the functionality that you need for a copy using libcircle, right? So walking the source directory, creating the destination files, copying the data over to the destination, and then finally updating the metadata. And so we like this setup. I reached out to the Los Alamos team that did this work and explained to them that maybe we could create a bigger suite out of this, and they were all excited about it. At the same time, they noted that people at Oak Ridge might be interested, so we got in touch with them, and then Oak Ridge pointed us to DDN, and so DDN got involved. And so from the outset, we had sort of 4 organizations collaborating on this software. We later changed DCP in some ways that I'll describe to make things a little easier, but this is where it all started. So what is Mpifyutils? Well, it's actually 3 things. So there's a common library that we call libmfu, short for Mpifyutils. And then there's a suite of pre-built tools that come packaged with the software. And then there's a common file format. And this file format turns out to be useful in that it allows the tools to interoperate. So the output of one tool can be the input of another. The library is there really to make integrating or adding new tools a little easier. So functionality that we think multiple tools could benefit from eventually work their way down into the library, and then that makes it easier to add or create new tools from that. And then the tools are MPI-based versions of sort of your common things like, CP, remove, ls, that kind of work. Within the common library, we have all these data structures and functions that are implemented. The main data structure that's there is this file list, which we call MFU list. And then there's all kinds of functions that operate on this list. But the idea of the file list is that you have a distributed stat information across the ranks, right? So imagine you have a large directory tree, and what you want to know is the stat information for each of these directories and files and symlinks. But it's too much information to store on one rank, or maybe it's not efficient to store in one MPI rank. And so this is kind of scattered across the different ranks. This is distributed list, right? And so, for example, one way you might generate a list like that is to use libcircle to do a walk. So somebody gives you that top path of D1, and then you use libcircle to sort of explore what that path looks like and distribute workout. All the processes end up with some random set of the stat information for the items in the file system. Right. We then have a number of functions that operate on that F list. So some of them are global operations, and some of them are local. Right. So the global operations operate on the collective communicator, which is MPI world essentially. Right. And so one of the example collectives here is the sort. Right, so you might have like a random list, a random distribution of elements on the left side, and maybe you want to sort those across MPI ranks so that they're in some order, alphabetical order, for example. The sort is a global collective you call, and so when you start, you end up with some random set of distribution, and on the right side, everything is now ordered alphabetically by a path name. Right, and so the library contains a whole lot of functions like this that you can use from the different tools. As of the latest release, these are the suite of tools that come sort of pre-built in Mpifyutils. They kind of break down into two sets. There's what we call the production tools, and those are kind of ready to be used by end users. And then there's the experimental tools. The experimental ones are sort of maybe early production or just there as example tools that you might build another tool from. But just to give you a flavor of what these are, I'll run through the production suite. So everything in black here, but so dbcast is a broadcast tool. It's a way to, given a file on a parallel file system, broadcast that file out to, say, compute node local storage on every compute node. So if you wanted to load a tarball from the parallel file system onto the SSD of every node, dbcast is a good way to do it. Right? It's written in a way so that you only read the data once from the parallel file system, and then you're using MPI to exchange the data across the nodes when you write it locally. DBZ2 is a parallel compression tool. So if you have a large file, especially like a large text file, and you want to compress that or decompress it, DBZ2 can help with that. dChangeMod is kind of like a parallel change mod and change group combined into one. dCompare is a way to compare a set of directories and files bytewise. DCP is the copy tool that I already talked about. Dedupe is a way to identify duplicate files on your file system. It does that in an efficient way to sort of use the hashing mechanism. DFileMaker is really just it generates a bunch of files and directory trees. It's really just meant for testing purposes if you want to instantiate a large directory tree that you need to work with. Defind is a way to filter a list into another list. So if you, for example, want to find all of the regular files that have a certain path name or component, you can start with an initial list, run it through defind, and then you end up with a subset list that shows you the matches. Derelink is to update a set of symlinks. Deremove is a parallel remove. Destripe is a way to restripe files on Lustre when that used to be a thing. The newer Lustre versions maybe don't require that so much. Desync is a way to sort of synchronize a source and a directory tree. So this is actually really useful to make backups. And the admins at Livermore use this very frequently when we get a new file system in. So when they're moving data from the old file system to the new file system, desync is the tool that they typically use to do that. dtar is a parallel tar. You can create a tarball or extract a tarball. And then dwalk is sort of like a parallel ls or parallel du to run on the file system. And then, so you can use these tools, you can sort of string them together to comprise like a bigger operation, right? So rather than having to write a new tool, you can use them in combination like this, often using the input and output options, right? So as an example, imagine what you would like to do is identify all of the files on your file system whose access time is 180 days or more, right? And then you'd like to delete them. So it's kind of like a purge tool. You want to find any files on your file system that people haven't touched in 180 days and delete them. You can do that using these three tools in sequence, right? So you can walk the path of your file system with dwalk and save all of that information with the output option, right? So it's basically saving the stat information. And then you can run dfind to filter that input list based on identifying regular files and whose access time is 180 days or more, and then save that subset list to another purge list. And then finally run DRM to read that purge list in and go delete the files, right? And so you can see how this is using this common file format I was talking about, and it allows you to sort of compose these tools in a way like this. Okay, I was going to jump into performance, but just before I do that, are there any questions? Anything here? Yeah, but
can I make a request?
maybe.
In the list of the experimental tools, you've got three. The last one's DSH, and that collides in name with quite an old but widely used tool.
Yeah, right. Yeah. Rename is basically what the request is there to pick a different name. Yeah, we can do that. Yeah, and it's not really. So I use that all the time. It's not really a shell in the sense that a normal shell, but what it lets you do, if you've reached your quota on the file system and you need to go delete some files to make room, DSH is a really handy way to do that. So it will walk whatever directory you give it, and then it will total up the bytes that are in there and the file counts, and it will list them by the directory that has the most in it, right? So it's sort of like a DU in that sense. But then you can run the remove operation. You can CD down into directories and pop back out, and then sort of list again, so you can figure out where your space is at. And then you can run the remove operation from there. And what it's really doing is it's invoking the same remove function that DRM does if you were to just run that by itself. And so actually DSH, even though it's experimental, I find that to be really, really useful. I use it all the time. But yeah, rename, yeah, we probably need the rename. And I probably should take the SH out of there, to be honest, because it's not really a shell. Yeah, I'm like,
Yes. I actually have two questions. One is, what is Mpi util? Is that potentially a proposal for the Mpi standard?
oh, no. Yeah, we initially called it like file utils. Of course, that conflicted because there's another file utils. So we threw the MPI on the front of there to make it clear. But yeah, I don't think that we need to standardize any of it. Just keep it as it's open source library. Yeah.
My second question is, the parallel system existed, you basically separate out meta data from the real data files. And what happens is, for data, you actually generates striking across smaller files to construct a virtual file so that you can have more parallel access to different stripes of data. But the metadata is centralized.
Yeah.
Right. For this kind of a distributed file, do you have a different way to looking at a different characteristics of the file system?
Yeah, so there's a couple of questions in there. So yeah, one question that has to do with the file system you're dealing with. So the tools in the library do have the capability that if you can identify that you're on GPFS versus Lustre, or even Lustre version X versus version Y, you can pick different algorithms, right? Because you can imagine creating a bunch of files on one version of Lustre. There might be a more efficient way to create a bunch of files on a newer version of Lustre, for example, right? And so if there are ways in the file system you can sort of introspect information to get the stat information faster than, for example, just doing a stat call, you can detect that and then use those back-end hooks. And so we do that in some cases. But yeah, as far as the metadata question, yeah, it depends on the file system as to whether the metadata server is distributed or not, right? So imagine if you have a parallel file system, but it's got a single metadata server, now you're just hammering on it from all these MPI tasks, right? And so you're really not going to get much speed up from that. But if you, it sort of depends on your parallel file system distributing the metadata in some way, and newer versions of Lustre and Spectrum Scale, GPFS, do that. And so you can actually get parallelism out of the metadata by if you have enough file system. But like NFS has problems that way. But yeah.
Maybe I missed the first part, but is that the file system itself is an ordinary POSIX file system?
It's, yes, so we're assuming a POSIX-based file system on the back end.
Okay, so in that case, the tools, the collection of some tools to manipulate the files. So there is a possibility to fail of any MPI-based and parallel running. So I'm curious that how do you recover, or do you have any lock system to make the consistency in that any?
Yeah, that's a good question. So I have a slide that sort of talks about that later in the talk. So I'll come back to that. But yeah, it's a really good question. And the short story is that we don't really do anything, right? So you kind of like some way to checkpoint your MPI job and then pick up where you left off. And we don't have that yet in the tools. But some of the tools kind of checkpoint themselves naturally, like DRM as you're deleting stuff. If it were to be interrupted, you pick up and you just delete what's left, right? So it sort of is naturally checkpointing. And desync sort of has a way that it can save checkpoints periodically. But not every tool in general can do that. But yeah, I'll circle back to that a little at the end too. All right, thanks everybody. All right, yeah, let me jump into the performance. So we did some scaling studies, and this was on Sierra. And so as a test data set, I was using exactly what I was explaining before, that single directory, 200,000 files, 128 megabytes a file. And we wanted to do three things. We wanted to use DCP to make a copy of the data set, and then use dChangeMod to change the group on all the files, and then DRM to remove the copy, right? And we did that test on Sierra, scaling it from 1 node to 1,000 nodes. So that ran from 40 procs up to 40,000 processes. Okay, so one of the things I should mention is the original DCP did all of its work asynchronously with libcircle. So walking and creating files and moving data was all sort of going on in parallel at the same time. One of the things we did when we rewrote DCP is we changed each of those to be a synchronous collective. So it runs slower than DCP used to run. But the reason we did that is because it makes those functions easier to incorporate in other tools, right? So if you have a walk tool or a walk function, you can just use that in other tools. The other side effect of that is that you can sort of time each of those independently. So now we know like what each of those phases cost. And so the tool will spit that out. And here I'm just plotting a bar graph of how long the copy takes, but the different phases of it. There's a walk where you walk the source directory, create the files, copy the data, and update the metadata. And then there's an other in blue there. The other is time external to the tool. And so this turns out to be your MPI launch time, really. And so what you'll see in a lot of these tools is the other cost is usually pretty small until you start to get up at the larger scale when the MPI launch is starting to take significant time, right? And so this is DCP, and you can see that it's getting good scalability, at least up to 3264 nodes. Most of the time is spent in the actual copy phase, moving the data, but that decreases nicely as you scale up until we saturate the file system, and then that gray bar doesn't shrink anymore, right? But the blue bar is increasing because now the MPI launch time is going higher.
Fantastic work. Let's say from the MPI's perspective, what do you think was the biggest scalability issues, like from communication or job launcher? Do you have any feedback for us on that?
Yeah, I mean, I think most of it is in this blue piece, which is the job launch. And I don't know if that's like the bootstrapping of the MPI job or just sort of getting the binary executables out to all the nodes. I didn't have a chance to analyze.
Okay, so was this an average of like 5 or 6 runs? If so, then like the cold cache effect might have gone away.
Well, it is an average over 5 or 6 runs, but they were in different allocations each time. So it probably still had that cold cache.
Yeah, I think
that's a good idea.
I think this is something that we had thought about when we were working on Avalanche.
Yeah. Right. Yeah, and just I finished up this slide. So I reran that serial copy test. This time I allocated a compute node so it could finish, right? And it took just about 13 hours, before we were estimating 14. So it was pretty close. But the best DCP time there is 93 seconds, right? So that was at 64 nodes. And so you're getting a speed up of like 500 times. So what used to take you 13 hours, if you were using CB, you can do in 2 minutes now, but you need some nodes.
So there is this tool called rsync, which was developed some time back. So did you try to compare the seconds like those kind of tools? Or?
I did. Well, I looked at. I think I looked at the code for that.
Okay.
But we didn't actually run comparisons.
Okay.
So.
The other question is, do you think, let's say, MPI IO could play a role here? Would that be beneficial? So thoughts.
It could help. So we use MPIO when we save that file, that input and output file that I was talking about, and we actually ran into a whole lot of problems with it, where we found that there was something we were trying to do. We're using external 32 format because we wanted the format to be a binary form that could also be read without using MPI. And we found that we were using 4 different MPI implementations. Each one of them, they're all supposed to write to an identical format when you use that. And we found that all 4 of them were writing to a different format, and none of them were right. so we had to, I think you guys fixed the bug, and we reported it to IBM, and there was OpenMPI also fixed the bug. But yeah, so MPIO is a little bit, there's some landmines in there that
Okay.
we decided to avoid later. But
Okay. So I think Nick Contini works on that. So maybe I'll ask Nick to talk with you later about
okay,
it. Thanks.
yeah, that'd be good. Yeah, and this is just a bandwidth chart of DCP. So this is just showing the copy time. The total bytes copied divided by just the gray portion that I was showing earlier. And again, you can kind of see that you've saturated up at 64 nodes. And I guess the important point from this, you'll see this on basically any parallel file system, you'll eventually saturate out the bandwidth. And the takeaway here is that once you reach that saturation point, you're not going to speed anything up by allocating more nodes, right? So you don't need to run with any more than 64 nodes for this. Here's the dechange mod. I actually ran this on 2 clusters. So on the left is Sierra. This is our Coral 1 system with GPFS, IBM Spectrum, MPI, and JS run as a launcher. And then on the right is Quartz. And this is using Lustre as a file system, and Mpifyutils and Slurm. And you can see these different trends going on. Some of this is because Lustre is slower on the right side, so you're starting from a higher point that it scales out better. But it seems like the JS run also, the launch cost is higher, so you really kind of suffer quicker from that, right? So if you look at like the minimum time to do this operation on the left side, basically once you get to 2 nodes, you're done. Everything starts to slow down after that. And on Quartz, you can go up to maybe 64 nodes, 32 or 64 nodes, and still get benefit, right? So there's variable there, but some of these short operations, it might be better to just run with small node counts. And then this is DRM, and there's a similar effect going on here. Although now you can see even the remove cost is getting higher, right? So we're starting to thrash the parallel file system in this case.
Excuse me.
So that you can end up with these sweet spots that you need. Yeah.
Yeah. Is there any impact of the file size on the normalized latency and bandwidth of the copies and?
Yeah, there is actually, and even the remove on GPFS, the file size can change the effect, right? Because the way they store small files in the file system is different than how they store big ones. And so, yeah, it's the cost to do a remove of a bunch of large files can be different than the same number of smaller files. Yep.
Thanks.
Yeah, there's a lot of variables in play. Okay, yeah, let me wrap up here. A few things to remember. These are MPI jobs, so you need to run them in allocation. Most of the things you're going to be doing as a single user, you might just get away with 2 or 4 nodes, but if you're sort of an admin moving a lot of data, or you have a really big data set, using more nodes is useful. You need to launch your job with the Mpi Job Launcher. Generally, you want to use all the cores that are available, except that it's good to leave a few free for the file system, because the file system is running some processes on your compute node too, and it doesn't do any good if you're busy spinning on the CPU and starving the file system from getting any work done. Most tools don't checkpoint the progress, the point I was making earlier, so you basically have to allocate enough time so you know the tool will finish. Some of the tools can leave things in a bad state, like DCP, if you get stuck halfway. Other tools kind of pick up naturally, like DRM and desync. You can't use the Linux pipe, so you can't like pipe them together like you would want to in a Linux shell. But the input and output options provide pretty good workarounds for that. And right now, to determine whether the tool succeeded or not, you just kind of look at the standard output, right? So we don't record the error code very well yet. But the tools are really built to run on any HPC system. So they're written in very basic C, MPI, and POSIX libc calls. So almost any cluster you're dealing with is going to be able to build these things. They're in SPAC. Greg will be talking about SPAC later. So it makes it real easy to install. And they're built to sort of run on any HPC system that you'll come across and work with. They currently work with Lustre, GBFS, NFS. Intel is adding Deos support now. The default algorithms, like I mentioned earlier, will generally work on any POSIX file system, but if you can detect the underlying file system and you know a faster way to do something, you can also code in a better algorithm for the file system you're dealing with. And so we have some of that in the tools. The takeaway, like when do you want to use these? For most of what you're doing, probably the standard Linux tools are sufficient and they're way easier to run. But when it starts to feel like that's taking a long time, then you could look at Mpifyutils. I threw some links up here where it's open source, so you can go download it. There's some documentation. And like I said, it's been a multi-organizational effort from the beginning. We had four people from the start, and more groups have added in. And so there's, I'm kind of representing the work of a whole lot of people here. But anyway, so that's the end. But before I finish, I wanted to also throw a big thank you out to the Mvapage team. As I mentioned earlier, actually on the right side, so this is the same data I was showing earlier, but now it's plotted by time. And it goes back to, 1969 there, but most of the files there are 1999 and later. So our file systems aren't that old. So this is people like migrating their data sets from one file system to another over the years. And stuff is getting deleted. So it's not a great representation, but what you do get the feeling for is that, these data sets are growing over time, which makes sense because they're going to correspond to the amount of memory you have on your systems. And MPI is what has enabled that, right? So, MPI has been around for decades, and it's allowed people to build these bigger systems and run jobs on those bigger systems. But, with that, people are doing big science. You saw in Dr. Boca's talk this morning that climate change, drug discovery for things like cancer, for COVID, right? Like these are having real impact. And it's all because of MPI, and that's really all because of groups like Mvapage, right? So it's actually the hard work of the students that are writing Mvapage that make all this happen. And it's really special, I think, to be like a master's or PhD student where your research can have such a direct and immediate impact on the world around you. I mean, the stuff you write gets released in code and then people are running it on the systems the next day, and it's actually improving science, and some great things are being done. It's unique to be in that situation, and the HPC community really appreciates all of your effort on it, right? So, personally, just a round of applause for the Mvapage developers. Thank you. And then I've got one more slide. I think in a way that you've been too successful. So I have, I have my work life and I love what I do for work, but when I'm tired of work, I like to watch sports, and that's Buckeye football and basketball games, right? And so each year the Big Ten, the ACC get together in a Big Ten ACC challenge, and last year Ohio State played Duke, who happened to be the #1 basketball team at the time. This was November 30th. And really, we just kind of took it to them. So as an Ohio State fan, it was fun to watch, right? So this is Zaghi getting a dunk, Justin Arns going for a layup. I think Malachi Branham getting another layup. Of course, I picked all these pictures. The end result is Ohio State wins that game 71-66, right? Upsets the #1 team in the country. When you do something like that, everybody rushes the court, right? So that's always a fun memory. But it wasn't the only memory I had from watching that game. This is a nationally televised game on ESPN. I stopped looking for a minute or two, and my girlfriend Leslie shouted, "Dr. Panda, Dr. Panda!" And I looked back at the TV real quick, thinking maybe you were at the game in the audience or something. But no, what's really going on is Ohio State's running a commercial on ESPN on national television and there's Dr. Panda on my TV in my living room. And so, Mpifyutils has now been so successful, it's bleeding into my sports life, which is supposed to be the area that I'm not thinking about work. So I just wanted to say, stop it. Yeah, thank you. Oh, yeah. Yeah, it was nice.
Thanks again. I think we'll have some time for questions.
Yeah, I can just meet me wherever if you have questions later. I'm happy to talk. So,
Okay.
Yeah.
So then let's thank again Adam, and we'll switch to the next talk. But before I start,